So here is our last unit, vectors. Okay, thank you. So, a couple of definitions to start with. What makes something a vector is that it has a magnitude and a direction. So if we have something that's just measured by its amount, like 5 kilometers without a direction, that's just called a scalar. But a vector has 5 kilometers to the north, gives us a direction and a magnitude. So a measurement and a direction. So distance and speed, they don't necessarily tell us which direction it's going in. But if we talk about something like displacement, displacement is from a starting point to an ending point, and this is something that sometimes when we're talking about speed and velocity, sometimes we talk about them as the same thing. Why are they different? Well, velocity technically often comes with a direction to it, making it a vector. So I want you to think through each of these. I'm going to give you some time for that, and I want you to think, do these things have a direction and a magnitude, or do they just have a measurement, or are they neither? So you can put an S for scalar, V for vector, and N for neither beside those. All right, let's see how you did. Outside temperature, scalar. Truck, scalar. Water, vector. Wind, direction only, so that one's neither. Vector. And the last couple on the next side, those are all vectors because they have a direction and a magnitude. So we represent a vector with a straight line and an arrowhead. That's what vectors look like. When we write things, we write an arrow over top. So here we have a line segment from O to P. You can have that arrowhead in the middle there, or if you want to put the arrowhead on the end, either way. So sometimes you'll see in textbooks vectors labeled. Some textbooks bold it when it's a vector. Other textbooks put an arrowhead over top of it. Sometimes I've seen it with a half arrowhead like that. That's how I like to draw them because it takes less time to actually lift up your pen and draw a whole arrowhead on there. So any of those notations will be fine. And we can write our vectors as a column vector, sort of like a column matrix. We put our x on top and our y underneath. So for example, this vector here looks like it's gone over 4 and maybe up 5. Then we would write that vector as 4, 5. And that vector we call a position vector because the 4 and the 5 are in reference from the origin. So anytime we do something in reference to the origin, we call it the position vector. So in the diagram below, the line OA represents the vector OA, and we could write it as 6, 3 because it's gone 6 to the right and 3 up. So here we talk a little bit about that notation, and we introduce another one. Sometimes in textbooks they underline it, or you can underline it. Again, I think I prefer the arrow over top, but any way that you denote it will be fine. But you have to denote it in some way. Bolding is pretty hard to do while writing. I guess you could just spend a couple seconds going over the V over and over and over again until it's really bold. But the little arrowhead over top would be fine. So the magnitude, in other words, is modulus of the vector is how long it is. So its length. And we denote that with absolute value bars, because really absolute value bars are a distance. How far away is 5 from 0? 5. So the absolute value of 5 is 5. How far away is -3 on the number line from 0? 3. So the absolute value is really just figuring out the distance of something. But now we're going to figure out the magnitude of vectors. And all we have to do is use the Pythagorean theorem. So if we had 1, 2, 3, 4, 5, 6, 1, 2, 3, 6, 3, and you wanted to figure out how long that vector is, well, you just need to make a triangle. You know this side is 6, this side is 3. A squared plus b squared equals c squared will be the square root of 45. So we can say that the magnitude of vector OA is the square root of 45. Some properties of vectors, we say two vectors are equal if they have the same length and the same direction. So that's going to be important. So A and B and C are all equal vectors here because they all go in the same direction and have the same length. It doesn't matter where they start or where they end as long as they have that same direction and same length. If you multiply a vector by any number, all that will do is change its length, but it will keep it parallel. So if I take a vector and multiply by 2, it's still parallel. If I multiply it by -3, notice these vectors are in this direction. The negative changes the direction, but it would still be parallel to the other vectors. We define a unit vector as a vector with a length of 1. So there's two standard unit vectors. One of them is going 1 unit to the right, and the other one is going 1 unit up if you're working in 2 dimensions. So these are called the standard unit vectors in 2 dimensions. We'll also have standard unit vectors as we go to 3-dimensional math in a bit. So here's the vector 6, 3. It can be written as 6 to the right and 3 up. So it's 6i and 3j. I don't know why they decided to use the unit vectors I, j, and then once we get to 3 dimensionals, k. Who decided to start with the letter I? Not sure. But that is standard. So it goes 6 in the x direction, 3 in the y direction. And so this is another way that you can write. And if you were writing this out, you would have to write that arrow over top the I and the j to say those are vectors as well. All right, so I'd like you to write each of these with i's and j's. Okay, check how you did. Now, the beauty of vectors is using vectors, we can solve mathematical problems that using our old methods of just geometry and trigonometry might become difficult to do. And vectors has some very simple rules that allow you to solve some very complex problems quite easily. So here we are going to introduce 3 dimensions. Here are the unit vectors for 3 dimensions. When drawing things in 3 dimensions, what you sort of imagine is you imagine taking, here I'll grab a piece of paper here. And on your piece of paper, you draw your x and y axes in 2 dimensions like normal. And then you imagine putting that piece of paper down on a table like this and adding a dimension straight up. That is your z-axis. And that'll create it in 3 dimensions. So what's happened here, can you imagine this piece of paper being placed on the table like that? Can you see that x and y axis on that piece of paper and then your z-axis going straight up from there? Can you visualize that? So when you drop something into 3 dimensions, this is still 90 degrees in here. And this is 90 degrees here. And all of those will be 90 degrees in between them, just in 3 dimensions. So now if you wanted to represent the vector -9, 3, 4 on here, you would go -9 in the x direction. That would get you to here. 3 in the y direction, that would get you to here. So this would be the point right here in my 2 dimensions. That would be -9, 3 on my 2-dimensional piece of paper. And then from that point, I need to go up 4 units. So if this is 4 units on my z-axis there, when I go up 4 units from that point, it's higher than the 4. Sometimes that's a mistake that when people are drawing that they end up doing in 3 dimensions, is they end up making that point right here because that's where 4 is on their z. But you have to imagine you're at this point on your paper and then you're going up 4 units from there. So the point is actually higher up there. And this would be your vector as a result. We're going to find that we like to write our vectors as column vectors. The math is a little bit harder if you use the I, the J, and the K, but you have to know how to work with both of those. Now, figuring out the length of that vector in 3 dimensions, at first it seems like this could be difficult. But if you go back to 2 dimensions, so I'm going to go in green, how far is it from 0 to -9, 3? This dotted line right here. Well, that just makes a triangle, right? That would be 9 on this side, 3 on this side, and you would do a squared plus b squared equals c squared. And I'm going to do it without simplifying it. If I did a squared plus b squared and then equals c squared and square rooted, that's how long that side would be without simplifying it, just writing it that way. Now the reason I write it that way is I want you to see when you're figuring out the red one, can you see that that still makes, this is still a 90 degree in there. That makes another right angle triangle. And if you did a squared plus b squared equals c squared there, so I'm going to call this my c, c squared is going to equal a squared. Well, a squared I'm going to call the blue line. That's just force. Well, no. I'll call a squared the green line, just so that the order is nice. A squared is the green line, which would be the square root of 9 squared plus 3 squared all squared plus the height, which is our blue line, which is 4 squared. What happens with that square root and the squared? They go away. And you get a really, really simplistic formula when you're going into 3 dimensions. It's just a squared plus b squared plus c squared equals d squared, in a sense. And you just have to do each of these dimensions, 9, 3, and 4. 9 squared plus 3 squared equals 4 squared, and then square root that. So if we want to find the length of this, the magnitude of v will equal the square root of -9 squared plus 3 squared plus 4 squared. 81 plus 9 is 90 plus 16 is the square root of 106. Find the lengths of these vectors. So this one's two-dimensional. The length of u would be a squared plus b squared. So you get 9 plus 16, which is square root of 25, which is just 5, which you might have recognized already as the 3, 4, 5 triangle. Here we've got -1, 5, and -7. So the magnitude of v would be square root -1 squared plus 5 squared plus -7 squared. Notice that when you have negatives and you're showing your work, they would need to be in brackets in order for that -1 to show that it's being squared. This is going to be 1 plus 25 is 26 plus 49. Square root of 75. Not that exciting. But the last one I think is exciting, because if we figure out the length of A, we get 36 plus 9 plus 4, which is square root of 49, which is 7. So how many sets of 3 numbers can you find that have nice answers? Sort of like, how many Pythagorean triplets do you know? 3, 4, 5? Any multiples of 3, 4, 5? So 6, 8, 10, 9, 12, 15. Do you know any other triplets that work out nicely? 5, 12, 13, yes. 8, 15, 17. That's not the one you're thinking of? No. There's 7, 24, 25, 9, 40, 41, 11, 60, 61. Anyways, there's a bunch of them. But now you can explore sets of 3 that add up, that work out nice. And your first one is 2, 3, 6. Did you know that 6 is the first perfect number? Can you tell me the 4th perfect number by tomorrow? Okay. Given v is equal to this, and the length of v is 10, what is A? Well, 10 would have to equal the square root of 3 squared plus a squared plus -7 squared. So we would have 10 is equal to the square root of 49, and 9 is 58, plus a squared. How could I work here? Square both sides. 100 is 58 plus a squared, so a squared is equal to 42. And a could be positive or negative square root of 42. How many people know what a perfect number is? Sorry, I threw that out there. No? A perfect number is a number whose factors other than itself, so the factors of 6 are 1, 2, 3, and 6. And if you take all the factors other than itself, it adds up to it. So 1 plus 2 plus 3 is 6. And since all the factors add up to that, it's called a perfect number. It was on one of the math contests? Perfect. Okay. Excellent. So here's some new notation for the unit vector, with a little hat over top. So we use that as notation that it has the same direction, but its length is only 1. So here we have 6, 3, 2. We already figured out that the length of u from before was 7. If we want to write a unit vector in that same direction, we're going to have to take that answer and divide it by 7. So our unit vector, one way you could write it is 1/7 of what you had before. So that's using that kind of notation. You could also distribute that 7 inside. And if you did a squared plus b squared plus c squared and take the square root of that vector, you would get 1. Or we could write this using our unit vectors. All those things mean the same thing. So we know that the length of that vector, since we figured out that length before, was 7. So now the unit vector, in order to have a length of 1, we would need to divide by 7. So we find a unit vector by finding the length of the original one and dividing by that. So I guess we could write a formula if we wanted to for unit vectors. Woo. So the formula for a unit vector is equal to 1 over the length or magnitude of u times u. Try these ones, get the unit vectors. Okay, here are the answers. There we go. So you could write, once you find the length of the vector, then you have to divide by that. So the length of in A was root 29. The length in B was root 61. I like to write it out in front. That way when the numbers seem at least nicer for longer, instead of writing it mixed in, but either way would be fine. And so in this last question, where you were to find a magnitude of root 7, you could find your unit vector first. And that unit vector has a length of 1. And then once you have that length of 1, to find something with a length of root 7, you would just have to multiply your unit vector by root 7. So we get a really not nice looking final answer, but you have root 7 over root 38 times your original vector.